Okay, so let us start. So welcome everyone to the Shannon channel. I'm really happy today to have Xiugang Wu from Delaware. And he's going to talk about information constraint optimal transport from Talagrand to Marton to cover. Thank you, Xiugang.
Okay, yeah, thanks very much, Salim, for the invitation and the introduction. So, it's a great pleasure to be here and talk about our recent work on information. It's basically in general optimal transport, and this is based on the joint work with my student Yikun Bai at Delaware and our collaborator Ivan from Stanford. So maybe to begin this talk, let me first explain to you what is optimal transport. If some of if not all of you understand, have you heard this before, as well as why we have the three names Talagrand, Marton, and cover appearing in the title. Okay. So optimal transport is optimal transport is a mathematical theory pioneered by the French mathematician Monge around 300 years ago. In his paper titled The Note on Land Excavation and Infill, Monge studies how to transport one pile of sands to another place with a prescribed shape in the most cost-effective way. So using a modern mathematical and probability theory language, Monge's optimal transport problem can be formulated as follows. Suppose you are given two probability measures, Pz and Py, which represent the two piles of sands, right, after normalization, and a cost function C, which assigns a non-negative number to each pair of Z and Y. Suppose you move from this Z to this Y, then the induced cost will be, given by the cost function of Z and Y. The Monge's question is to basically minimize the expected cost of moving Z to Y over all the possible function T's that maps Z into Y. Okay, so while Monge's formulation looks quite nice and it works well under this two power of sands problem, it turns out that requiring Y to be a function of Z can be too restrictive. Restrictive in some cases. For example, when Pz and Py are both discrete probability measures, you may or may not be able to find a deterministic function T that maps Z into Y, right? So this is a very earlier appearance of optimal transport. And around 200 years later, the optimal transport problem was rediscovered by the Russian mathematician Kantorovich. Actually, not only Kantorovich rediscovered the problem, but also he realized the importance to relax the formulation of the problem and allow for all the mappings from Z to Y, including the random ones. In particular, in Kantorovich's formulation, you are still minimizing this expected cost, right? But now the search domain is over all the possible couplings of Pz and Py, where each coupling of Pz and Py is nothing but a joint distribution whose marginals are given by Pz and Py respectively. Okay. So by the way, please feel free to stop me if you have any questions. Okay. And
yeah, I wanna
yes,
clarify one thing. So is it like the distribution of Z and Y are already given, and your job is to find this cost function?
No, you're right in the first sense. The Pz and the Py are given as it is, and this cost function is also given. Your job is to, given Pz and Py and C, your job is to find the optimal coupling that makes this expected cost as the least. So basically, it's a minimization problem with the parameters Pz, Py, and C all given, and your goal is to find the optimal coupling.
Okay.
Mm-hmm.
And another question, what was the relaxation here? You mentioned that it's a relaxation of the original problem.
Yeah, exactly. So the relaxation here is that in Monge's formulation, Y has to be a function of Z, right? Imagine Z and Y are both discrete measures, right? You may or may not be find a function that maps Z into Y, right? So maybe an even trivial example is when Z is discrete, Y is continuous, right? So any function of Z will give atoms, in the mathematical, theoretical measure theoretical language, the Y will inevitably have some atoms, cannot be a continuous distribution anymore. So you may or may not, yes.
So in some sense, you allow Y as Z to be like a stochastic function of.
Exactly. So Y, so you can really think of Kantorovich formulation as allowing for all the stochastic mappings from Z to Y, versus in Monge's formulation, right? So the mapping can only be deterministic. And later, a breakthrough in the field of optimal transport is basically to give some conditions on which the optimal transport turns out to be indeed deterministic. And there's some conditions that's actually only known, a couple of decades ago. It's considered one of the breakthroughs in optimal transport theory. And we'll also mention that later towards, maybe in just 10 or 15 minutes, we'll see that as well. Okay.
I just have a question. So in the first formulation, in the deterministic case, like this expectation was over what? Like there, I know over the coupling, but here it was over the distribution of Z and Y.
Exactly, because whenever you fix the function that links Z with Y together, right, you naturally already establish a joint distribution between Z and Y.
Oh, okay.
So, right. So, yeah. Okay, very good. So, and today actually optimal transport, starting from those two very simple formulation, optimal transport has evolved into a fertile field in mathematics today after generations mathematicians' efforts. This includes, in addition to Monge and Kantorovich, this also includes Koopmans, who actually won the Nobel Prize in 1975, jointly with Kantorovich, and Danzig, who, as you know, pioneered linear programming in the context of studying optimal transport, and many others, including most recently Villani and Figali, who were awarded the Fields Medals for their contributions to optimal transport. And accompanied with the rich theory of optimal transport are its far-reaching applications. And up to now, optimal transport has been known to have a wide range of applications, or have deep connections to a lot of disciplines such as economics, geometry, quantum mechanics, optics, etc., etc. And more recently, it has received renewed interest due to its increasingly many applications in imaging sciences, computer vision, and machine learning, where the most prominent example is probably given by the most recent generative model based on optimal transport, or the so-called Wasserstein generative adversarial networks, or simply Wasserstein GANs. So, however, in this talk, we do not plan to propose yet another application of optimal transport. Instead, given that we're on the Shannon channel here today, right? So instead, what we're going to explore today is the bidirectional interactions between optimal transport and information theory. We'll show that on one hand, the optimal transport theory can be enriched by studying problems arising from information theory. And this leads us to new optimal transport setups, distances, or inequalities, I will show very shortly. And conversely, these new findings in optimal transport theory will allow us to obtain new results in information theory as well. For example, it will allow us to derive some old and new concentration of measure phenomena through the information theoretical methods, as well as allow us to derive tighter capacity upper bounds in the field of network information theory. So in particular, here is the outline of the rest of this talk. Basically, we'll introduce a new optimal transport setup, which we call the information constraint optimal transport. And what we'll first do is to derive the so-called transportation inequality that upper bounds the transportation cost under this new setup. Okay, and it turns out that our new transportation inequality strengthens and generalizes the celebrated Talagrand transportation inequality. And actually, one of the reasons why Talagrand transportation inequality is so celebrated and interesting and fundamental is, I guess, in my opinion, is one of the reasons is because, it can be used to derive the concentration measure phenomenon or result in the Gaussian space. And this deep connection between transportation and the concentration measure was actually pioneered by information theorist Carlotta Marton around the, I guess, 80s. And this is also, I guess, appearing in her, citation for winning the Shannon Award a few years ago. So in the second part of this talk, we're going to show that our new transportation inequality can be also used to derive, to recover old and new concentration measure results. But now in this case, the result will be on the sphere instead of in the Gaussian space in the Talagrand sense. So we'll basically discuss why this happens and and how this connection between transportation and the concentration appear in the sphere as well. So that's going to be the second part of this talk. And lastly, we'll show that our new transportation inequality also finds interesting applications in network information theory. And in particular, the inequality can be used to resolve a long-standing open problem posed by Cover regarding the capacity of the relay channel. So let's first talk about the transportation inequality. And for this, we'll focus on the case when the two probability measures Pz and Py are defined on the n-dimensional Euclidean space, and the cost function of Zn and Yn is defined to be square of the Euclidean distance between Zn and Yn. Okay, so under those assumptions, you minimize, right? So you minimize the expected square of the Euclidean distance between Z and Yn over all the couplings of those two measures, right? And then if you take the square root of it, the resulting quantity you typically denoted by W2 between PZN and PYN is widely known as the Wasserstein distance, and in particular quadratic Wasserstein distance, because here you basically take the square of it and then take the square root of the optimal value. And indeed, it's easy to verify that this quantity W2 between PZN and PYN satisfies all the axioms of the distance metric, and therefore it introduces or defines a distance metric on the space of all the distributions PZN and PYN on in the Euclidean n-dimensional Euclidean space. Okay, so one of the central topic in optimal transport theory is to derive the so-called transportation inequalities that upper bound the transportation cost. And for example, the celebrated Talagrand transportation inequality states that if PYN is standard Gaussian, and if PZN is absolutely continuous with respect to PYN, then the square of the Wasserstein distance is always upper bounded by 2 times the KL divergence between PZN and PYN. And this inequality will be tied if and only if PZN is a shifted version of PYN, namely it shares the same covariance matrix, but with a different mean. So I guess a remarkable feature, yes.
So I might have missed what you said. So what is the inequality P of Zn is less than P of Yn? What does that mean?
Oh, so this is to say, this is absolutely continuous in the sense that, if a set on this measure and this measure has, probability 0, then under this measure, it has to have 0 as well. You can basically think of, if it's continuous, right? So a very rough interpretation of this notation is to say, basically, if there's no, if on the specific, interval, this has no measure, then PZN cannot be chosen to have measure on that on that interval. So basically, if you actually, this is a very good question. If you think about it, right? So if you look at the measure theoretical definition of KI divergence, this KI divergence is actually defined if and only if this is satisfied. Basically, it means that, if this happens to be 0, but this is non-zero, right? You will get into trouble, right? You will get into some infinity like issue, right? So, so this is basically, a technical condition for the right-hand side to have basically have physical meaning. Yeah. And yes.
I just have a question. So to make sure I well understood. So
sure.
Wasserstein distance is the optimal value of the cost function?
Exactly. So basically you minimize the expected cost, right? And you get a number and take the square root of it, and that is defined to be the Wasserstein distance. And you might be wondering, why should we take the square root of it? I mean, the purpose of taking, if this is P in general, then you should take 1 over P, and this is called the pth or the Wasserstein distance. If this is 2 and you take a square root of it and you get a quadratic one, you take the square root to compensate the square within the expectation, so that the resulting quantity will define or will introduce a distance, right? So those, right? So basically, you can really think of to define this distance, you need to do some minimization job. So it's not, like there's no explicit form for you to calculate that, but you have to find out the minimum expected cost, and then take the square root of, take the pth or the square root of it, and then the resulting quantity will be defined to be the distance. Okay.
Okay. Yeah.
Mm-hmm. So, as we said, a remarkable feature of the Talagrand transportation inequality is that it connects the Wasserstein distance with another fundamental divergence, right, in information theory, this so-called KI divergence, right? And this observation actually was utilized to derive the concentration measure, as we will show later, in a Gaussian space. Okay, so that's basically the first remark. And also it's worth mentioning that, going back to, I guess, Salim's question, or someone else's question, even though here we have relaxed the definition of Wasserstein distance to allow for all the random mappings from Zn to Yn, right? But as one of the breakthrough, I guess, in 80s, right? So there's a very famous Brownian theorem, which says that under this assumption, Yn is substandard Gaussian, Pzn is absolutely continuous to Pyn. Under this assumption, as well as the cost function choice to be the Euclidean distance square, under these assumptions, even though you have allowed for random mappings from Zn to Yn, it turns out that the optimal coupling that achieves this minimum is indeed given by deterministic mapping from Zn to Yn. Okay, so that's the second remark, right? So the optimal coupling that attains the Wasserstein distance is actually deterministic mapping. And this actually brings up the natural question that what if you desire some randomness, in the mapping from Zn to Yn? And I'll justify why sometimes, the randomness of the mapping is desirable, right? So different people have different justifications. It turns out that we have our own justification, while, machine learning people, which make use of this Wasserstein distance, extensively in the past few years, they also have their own justification. But at this point, so far at this time being, my problem is, the problem for us is to say, can we find out a concrete or a new setup of optimal transport, so that the optimal coupling end up being a randomized one, end up being a stochastic mapping instead of a deterministic mapping. So that's the problem faced by us at this point, and later we'll justify why the stochastic mapping sometimes is desirable and what is the implication or application, right? So if the mapping is stochastic. Okay, so and for this, so what we'll do is that we'll introduce the so-called information constraint versus distance between those two n-dimensional measures, right? So the way we define it is to say, as usual, we'll minimize the expectation of the square of the Euclidean distance over all the couplings, right? And then take the square root of it just as before. But now with a constraint, the constraint is that the coupling, the mutual information under the coupling cannot exceed some pre-specified, threshold, let's say capital R, right? And it's actually quite easy to verify that precisely because of this constraint, right? Precisely because of this constraint, in general, the mapping from Zn to Yn cannot be deterministic anymore, right? Because in general, think about if Zn and Yn are both continuous, and if the mapping is deterministic, then in general the mutual information could blow up to past infinity, which violates this constraint. So basically, you can really think of this constraint as a constraint which forces the mapping to have some randomization in general. And also, for the same reason, you can also show that, because of you have a mutual information constraint imposed on the coupling, in general, when R, for finite R, if you take a PZN, if you look at the Wasserstein distance in the constraint sense, in the information constraint sense, if you look at the distance between PZN and itself, this is in general not equal to 0 anymore, right? Why? Because if this is 0, then Zn has to be equal to Yn, right? Very roughly speaking, Zn has to be equal to Yn. But in general, if Zn equals Yn, this mutual information will blow up to past infinity, which means that, this quantity is actually, strictly speaking, is not a distance metric anymore, because this is so-called coincidence property or coincidence axiom associated with, any distance metric has to satisfy. So in general, this is not a distance metric, but still, with a slight, abuse of notation, we still call it information constraint versus distance between those two probability measures. Nevertheless, you can verify that this quantity indeed satisfies all the other axioms of distance metric. For example, symmetric one, triangle inequality, right? So only this as one exception. Okay, so, and also, if you think of the coupling as your optimization variable, right? Then the constraint is actually a convex in terms of coupling, and expectation you can verify is actually linear, right? So in general, this is a convex optimization problem, and therefore you can equivalently write this constraint optimization problem as the unconstrained one. Well, the only difference is that now, right? So the objective function will be replaced by the expected cost, taking the square root of it, plus lambda, some lambda, times plus lambda times the mutual information between Zn and the Yn. In other words, the difference between constraint and unconstrained version is that you replace the original cost, expected cost, with the so-called cost and mutual information Lagrangian, right? So this is the equivalent formulation, and it turns out that different lambda will correspond to different capital R here. Okay, so why do I want to mention this? I want to mention this because, very interestingly, after we introduced this framework and studied different properties such as information, such as transportation inequalities that upper bound this quantity, after we almost finished this work, we realized that, this equivalent formulation has received extensive attention in machine learning community in the past few years. And and also it generally appeared the name entropy regularized optimal transport in the machine learning literature because you can really think of this mutant information as the chaotic divergence or relative entropy. That's why they call it an entropy regularized optimal transport. However, the motivation from the machine learning community is mainly motivated by the computational considerations. In other words, it turns out that a lot of cases, if you want to calculate the Wasserstein distance from the data, imagine Pn is the empirical distribution from your data, right? If you want to calculate, let's say, fitting a generative model, you have, you want to check how much is your generated distribution, what is the distance of the generated distribution with respect to the empirical distribution. If you evaluate that in terms of the Wasserstein distance, right? Without this information constraint or without this, regularization term, it generally appears to be very hard computationally. But if you regularize it by this mutant information, it turns out that the evaluation could be a lot easier. So, however, our focus here is not, focused on the computational issues. Instead, our focus is on developing new transportation inequalities that upper bounds this information constraint of Wasserstein distance, and to explore the connections between our inequality, transportation inequality, to the concentration measure domain, and as well as to network information theory in particular. Okay, so here's maybe the first main result of this talk, which is a transportation inequality that applies to the information constraint Wasserstein distance. And basically, this inequality states that if Pyn is standard Gaussian and Pzn is absolutely continuous with respect to Pyn, exactly the same condition for Talagrand inequality, right? Same condition. What we can show is to obtain an upper bound of this information constraint distance by the right-hand side, right? By this expression. And this expression is basically in terms of 3 parameters, right? First parameter, the second moment of Zn. Second parameter, entropy of Zn. And then lastly, the information constraint, capital R, right? So, and we can also show that this inequality is tight whenever Pzn is isotropic Gaussian, with an arbitrary mean and sigma squared times an identity covariance matrix. And compared to the Talagrand, transportation inequality, this inequality is tied for a wider range of Pzn, not just for Pzn being a shifted version of Pyn. Okay, so
I have
actually,
a question.
Yes.
So does it make sense, or is it interesting to take R go to infinity here and see what happens?
That's an extremely good question. So that's what I'm going to do now. So if you take R to be positive infinity, right? So by definition, if you take R to be positive infinity, you kill this constraint, then the information constraint Wasserstein distance reduces to the vanilla case, right? So if you take R to be positive infinity, left-hand side becomes the regular Wasserstein distance. For the right-hand side, if you take R to be positive infinity, this term will get killed, right? And this product will become 1. What you arrive is this corollary. The Wasserstein distance will be upper bounded by this expression where R is eliminated. And it is tied whenever Pzn is isotropic Gaussian as before. And the natural exercise to do, of course, would be to compare this right-hand side to the right-hand side of Talagrand inequality, right? Which is 2 times the chaotic divergence between Pzn and Pyn, right? It turns out that this right-hand side is indeed always tighter than, in general, tighter than 2 times chaotic divergence. In other words, this inequality indeed sharpens Talagrand 1 for any Pzn. And also the inequality itself is tighter for a wide class of Pzn, as we just mentioned. And interestingly, it turns out that this inequality indeed appeared actually not not very old result. It actually appeared previously in the 2012 result by Bakri et al. And now it's basically included as a corollary of our information constraint transportation equality. And what is perhaps more interesting, in my opinion,